So this is from Andy Jones and Annie Van Hattelo in 2017. And this is kind of, okay, all very good. Tell us why this is important. I've kind of hinted at this a little bit, but let's really get into why this is important. The power-time relationship is a fundamental concept in exercise physiology for two reasons. First, it provides a framework for exploring and understanding skeletal muscle bioenergetics and the metabolic and cardiorespiratory responses to exercise. And second, it provides a powerful tool for fitness diagnostics, monitoring of the physical impact of interventions such as training and putative ergogenic aids, and performance prediction in continuous high-intensity endurance exercise. So in other words, it gives you far more than you'll ever see from a maximal lactate steady state or even from a respiratory compensation point identification. Because if I monitor the power duration curve, not just the critical power itself, but the curve itself, I can start to see where the changes are happening in that curve. And therefore I can start to understand what's going on bioenergetically within the tissue. And then I can monitor that curve and therefore by definition the critical power which sits on that curve in response to training, in response to ergogenic aids, in response to clinical conditions. So where is the critical power? Well, let's have a look at this data. And again, this is from Walsh and colleagues, published in Sports Medicine. It's a while back now, but it's a really nice graph. So same thing occurs. They haven't put the data points on, but here you've got your power duration relationship. You get the hyperbolic, and you start to see that this flattens out. This line here represents what's called the asymptote. The asymptote fundamentally reflects the point where this curve no longer keeps changing. The point where this curve no longer keeps changing, in other words, there is no change in the relationship between power and time, is critical power. It is critical power. So clearly you can see that this is unsustainable up here. It's much, much more sustainable down here. So this curve will never reach zero. It will flatten out. So once it flattens out, the asymptote of that point, which is this line here, and they put it in quite conveniently at 200 watts, is the critical power. I'll show you how you get to that in a moment. Now, you may be wondering about, well, okay, it's the critical power. How does this relationship look across different groups or populations? Well, this is a really nice data set to kind of help you with this. This is from Dave Paul and colleagues. Now, Dave Paul is really at the forefront, along with Andy Jones, of our understanding of the critical power model. So the same thing, you've got power duration relationship. So here you've got trained athletes, and you can see this perfect hyperbolic relationship. We can't quite work out where the critical power is because it doesn't quite level out. We haven't got the asymptote here. But one would hazard a guess, in this example here, it's probably in the region of maybe, let's say, 225. Here in our younger athletes, you'll notice something that's quite interesting, that the sustainability, the power being produced at the same workload. So if I take an arbitrary workload, so I'm going to take 300 watts here. So the duration for 300 watts is in the region of, for these guys, it's what's that? Let's call that I'm going to call that 250 as a rough arbitrary one. If I come to 300 for my older trained, I come down, can you see the difference? It's 120 watts. So by definition, this curve is pulled across. So the critical power, again, we haven't got the asymptote. You're looking in the region here of probably about 250 watts. But if I come down to patients that have got COPD or chronic heart failure, look at the effect. Really significant effect that we see across all workloads, therefore all fatigue-based mechanisms. And the net result is the critical power. You can almost see the asymptote in this population group here, and it's about 50 watts. The asymptote here, it's probably in the region of 90 watts. Massive difference. So it really does allow us, the understanding of power duration relationship really does allow us to understand bioenergetically what is going on in our population group, and the critical power is the function of that point, which is it defines that sustainable exercise, the exercise where we can get steady state. So we go back to Andy Jones again, and just kind of reinforce this as a little bit. And it goes to this. It says, well, look, physiologically critical power is important because it defines the boundary between discrete domains of exercise intensity, which we've already referred to. Below critical power in the heavy domain, steady state values for muscle metabolism, that is phosphocreatine concentration and pH and blood lactate and pulmonary oxygen uptake, can be attained. So we know we can get a steady state. It comes at a cost because you're now developing a slow component, but you will still get a steady state. It's not to say that that's, you know, it's not difficult exercise. It's pretty hard work in the heavy domain, but it is sustainable. And this is what we see. Now, we've seen this previously. This is from Harry Rossiter's group based out at UCLA. So here we've got duration on the x-axis, though we haven't got the time points on here. But what you can see, which is fundamentally important to this, is here's pulmonary VO2. So this is at rest. Now we have our square wave transition. So this is what we call the phase 1 response. Here's the phase 2 response, and we get a steady state. What they've done at the same time is they've recorded the PCR concentration in real time. And what you can see is that the PCR concentration, now remember that the PCR concentration will only start its decline at the point where we get the square wave transition in ATP turnover rate. So this graph, if we actually transition this across and lay it at the point where the transition comes, is pretty much a mirror image of the pulmonary VO2 at the onset of exercise. So in other words, the primary substrate that is being used in moderate intensity exercise to get us to steady state is PCR. Once we're at steady state, it's aerobic based metabolism. And as we get close to the steady state, the rate of decline in the PCR concentration starts to fall. In other words, it starts to become sustainable based exercise. When we go into the heavy domain, same thing applies. Here it is, we get the square wave transition. Here's phase 1. Here's phase 2. It's a little bit hard to see. So what they're saying here is they're putting this line in and saying, well, this is theoretically, the VO2 is starting to level out. So this is what the steady state exercise should look like. Now what you get is you get this slow component. So this area between what the VO2 should be doing and what the VO2 response is, this area under the curve refers to the fast twitch fiber recruitment. Now look at the PCR response. It is not a perfect mirror image, but it's pretty good in terms of the square wave transition. The reason it's not a perfect image is because it does, but it's difficult to see it. It primarily reflects this area above the curve, right? So it primarily reflects this slow component. So it's a pretty good mirror image. It's perhaps not quite as clear as we saw in the other moderate intensity exercise, but it's pretty good. And so again, it reflects the dynamics of the VO2 response, but we still get a steady state condition. You can see there's a steady state in pulmonary VO2, and you can see there's a steady state here in PCR degradation. But Jones then goes on and again is helping us understand that, well, okay, if we go above critical power, and that's in the severe domain, these variables do not demonstrate steady state behavior. Rather, despite the external power output remaining constant, muscle efficiency is now lost. It's reflected in the development of the VO2 slow component, and this drives VO2 to its maximum value at the limit of tolerance. In other words, we go to the point of volitional exhaustion. So what does that look like? So this is severe intensity exercise. This is Mark Burnley again. And we've got a number of different scenarios. Now, this is the really important point to understand. In all of these examples, and there are 4 responses here, these are all in the severe exercise domain. That is all exercise above the critical power. What this tells us is that this black trace here is the one that is closest to the critical power. And this data set here, these little triangles, is the one that's closest to the VO2 max. In other words, we're moving further away from what was a steady state response. This is not steady state, but we're moving further away from the critical power, which is the highest sustainable steady state response, to almost being at VO2 max. So the net result is when we look at the PCR degradation rates, they again reflect what you're seeing in this VO2 response here. Look at the PCR decline. It's really, really rapid. In all of them, they pretty much end up at the same point. Okay, so there's a real significant decrease because you've got non-steady state exercise, but the rate of decline reflects the intensity of the exercise. So in other words, the rate of decline in this block here, which is a 12-minute period of exercise, you've got a much slower rate of decline. It's still maximal compared to what you've got here, where they're hitting volitional exhaustion in about 3 minutes, that you can see here in the PCR degradation rate. So again, it really reflects this non-steady state based response. Were it steady state, the PCR concentration would not keep declining. It's pretty much hit zero in all those conditions.